So today we're going to start taking a look at 1.5 polynomial functions and complex zeros. So the first thing that we're asked to do is graph this on the coordinate plane and identifying the following. So I don't have the TI Inspire calculator on here, so I'm just going to go to Desmos and graph this. You can try graphing on your calculator, otherwise Desmos is fine for today. So x minus 2, then we have x minus 2, and then we have x plus 3. So if I graph this, I can look, and here's a couple key points. Okay, so if I go back to here, I know it crosses at -3 and +2. Let's see, what was that intercept there? Maybe I'll get that. 0, 12, which is, I think, off this graph, so way up here. So it kind of went down, it comes up and crosses. And then did it come down and it just hits there. So it hits there and bounces back up. So the x-intercepts, where did it cross the x-axis? Well, it crossed right here and right here. So it crossed at x equals -3 and x equals 2. What is the degree? So a reminder, degree is the highest power. So if I was to multiply this out, we'd have 3 x's, so it's degree 3. How are the factors related to the x-intercepts? Okay, well, for example, x minus 2 is a factor, and it crossed at x equals 2. X plus 3 was another factor, and it crossed at x equals -3. So I would say the intercepts are the value that make the factor equal 0. Because if I plug it in here, -3 plus 3 is 0. If I plug this in here, 2 minus 2 is 0. So what is different about the behavior of the graph at x equals 2 and x equals 3? What do you think makes that happen? Well, let's see. At x equals 3, it crosses the x-axis. And at x equals 2, it bounces. Well, when I look at that, there are 2 factors of x minus 2, and it crosses, there's only 1 factor of x plus 3. So next graph this next one, x minus 2 cubed and x plus 4. X minus 2 cubed. And we have, what was the other one? X plus 4. All right, so this looks, well, let's see, I'm guessing it crosses at -4 and 2, but it kind of does a weird curve there. Whoa, and then it goes really low. I don't even know how low that is. Let's see, -134.6. So it crosses at -2. No, I did that wrong, sorry. It crosses at +2 and -4. All right. And then it kind of came way down, and then it does this weird little jag right there. So what are the x-intercepts? Well, it crosses at x equals 2 and x equals -4. Now the degree, well, I notice there's a 3, so there's 3 x's in another one, so that makes it degree 4. What do you notice about the behavior at the x-intercepts? So at x equals -4, it crosses. And it's not that weird parabola from above. What could I call that? X equals 2. I don't know, it kind of squiggles, maybe we could call it. All right, and then this last one, let's graph it. So we have 1/2. And then what do we have? X plus 3, so I bet it crosses at -3. And then we have x plus 1. And then we have x squared plus 4. So it only crosses twice, at -3 and -1. All right, so it kind of went down, and then no zigzags or anything. It just kind of went up, more like a parabola. So what are the x-intercepts? Well, this would be, where does that equal? 0. So that's at x equals -3. X plus 1, what makes that equal 0 is x equals -1. But here, if I solve this, there isn't anything squared that'll give me -4. So there's only the 2 x-intercepts. In the degree, there's 2 x's, 3, and 4. So how many solutions are there to this equation? Well, there's got to be really 4 solutions, because there has to be some sort of answer here. Now, what you might remember is that, like tying into number 4, some solutions or zeros can't be seen on the graph. So if you remember from last year from advanced algebra, a parabola can hit it once, a parabola can have 2 real zeros, or if it doesn't cross it at all, those were where we called it imaginary. So this had 1, this one has 2, and those were imaginary. So now we're just dealing with polynomials, and they can have imaginary too. So we started solving this one. -4 minus 4, x squared equals -4. And does anybody remember when we square root something, we use that imaginary, so the square root of -4, the square root of 4 is 4, but since it's negative, we'd say it's 2, and then we add that imaginary. And then when we square root something, we do the plus and minus. So this one actually has those 4 zeros. So can a quadratic equation ever have one real and one imaginary solution? And I'm going to say no, because when you square root a negative, it's always plus or minus. So for example, if I had x squared equals -9, I square root it, it's going to be plus or minus 3i. If my factor was x minus 25, x squared minus 25 equals 0, or plus 25, I'd subtract the 25. X squared equals -25. I square root it. We have plus or minus 5i. So those imaginaries always come in pairs. So a couple things about this then as we start to summarize this. A polynomial function here, which we've been talking about for a while, these polynomial functions. So they are going to have a higher power. So they're not just the x squareds anymore. We're going to have to the power of 4 to the power of 5. So now when we take a look at this here, we're going to see how those factors relate to where it crosses. So it has an intercept at x, a, and 0. So again, this is like saying if a factor is x minus 5, we say, well, where does x minus 5 equals 0? Well, it's when x equals 5. So it crosses at that coordinate of 5, 0. So this next one here, let's say we have a polynomial right here. All right, and it crosses at -2, 0. So right here, here, and here. All right, so what are those linear factors? Well, if it crosses at -2, it's x plus 2. Cross at 0, so that's just x minus 0. Crosses at 1, so x minus 1. And 2, so x minus 2. And now you might say, well, x minus 0, well, that's just x. So I could put that one in front and have x plus 2, x minus 1, and x minus 2. Now, one thing that we're going to talk about here is, do you see how both of these end down? It ends like a negative parabola. So I'm going to have to put a negative in front since both of those ends go down. But we'll be talking more about this in the next chapter. Now multiplicity. Back up here we talked about how this first one had 2x minus 2 factors and it bounced. This one had to the power of 3 right here. And it did this weird squiggle. And then if it had just like a single factor, it just crossed through. That's what is called the multiplicity. So if it, for example, this one is a 10th degree polynomial. So here's 4, 5, and another one. So it's going to have 10 zeros somewhere. So x minus 0, since that's just a single x, it has a multiplicity of 1. Negative 3, since that's the value that would go here to make it 0, it has a multiplicity of 4. And 2 minus 2 is 0, has a multiplicity of 5. Now, real zeros with even multiplicity are tangent. So that means if it's an even multiplicity, it just does that bounce. And it could bounce positive or it could bounce negative. Odd multiplicity greater than 3 have a point of inflection, which I like to call, it does that little squiggle. So it kind of comes up and it does a little squiggle, or it can come down into a squiggle. So when we look at this next one here, x equals negative 3. So or x equals negative 1, it's a squiggle. So it has a multiplicity of negative 3 with a point of inflection. Again, I like to use just the word squiggle on the x-axis. So again, that's where it changes from concave up to concave down. X equals 1 has a multiplicity of 1 because it passes through. And this x equals 3 has a multiplicity of 3, and the graph is tangent, or I like to say it bounces on the x-axis. Now the other thing that we talked about way up here, complex answers. So when we square rooted that negative, they come in pairs. So again, complex numbers can be an a plus bi. So if there is one that has an answer of 3i, the other pair is negative 3i. If it's 2 plus 5i, it's 2 minus 5i. Most of the time we see our answers just like this. Every once in a while you'll see it with the real and the complex part, but just know that they come in complex conjugates. So a polynomial function is given by p of x equals ax cubed plus bx squared plus cx plus d, and it gives us the x-intercept. Okay, if 2.3 minus 15i is a 0 of p, what do we know about the other solutions? Well, there has to be 3 solutions because it's of degree 3. So we have x equals 1.7, and then our other one is 2.3 minus 1.5i, and since they come in complex conjugates, it's got to be 2.3 minus 1.5i. So there are the 3 solutions. Now, the last thing we're going to do is review how to find the degree. Now, we talked about finding the common differences here. So again, that looking at the rate of change, and we can see that these are going up by 1s on all of them. Now, we talked about linear and quadratic, but it keeps going. If the first difference are constant, it's linear. Second difference, it's degree 2. Third distance, it's a cubic. But again, we have to remember that it's equal interval input values, meaning the x's are going up constantly, which they are. So this one is going up by 3, down by 1, up by 1, up by 3. So if we look at this one, it's going down by 4, up by 2, up by 2. This should be going down by 3, I'm sorry. So then it's going up by 2 here. So, yeah, 5 to 2 is negative 3. So the second difference, so it is a quadratic. if we look at this next one, again, these are equal intervals. So we can check those differences. Down by 3, down by 3, down by 3, down by 3. That's constant, so it is linear because it's the first difference. Now let's see, 26 to 7, down by 19, down by 7, down by 1, down by 1. Let's see, 19 to 7, negative 7, so that's going up by 12, up by 6, up by 0. So down by 6, down by 6. The third is the same. So this is a polynomial of degree 3.